Imagine standing outside on a clear night, far from any city, far from any light. The sky above you is not black. It is deep, almost violet, and it is filled, genuinely filled, with stars. Thousands of them visible to the naked eye, millions more dissolving into that soft luminous haze along the band of the Milky Way. And in that moment, something remarkable is happening. Light is landing on your retinas, ancient light, photons that left their source thousands, sometimes millions, sometimes billions of years ago. You are not looking at the sky, you are looking through time. Now here is the thing that keeps physicists awake at night. Everything you can see, every star, every galaxy, every glowing cloud of gas, and every burning point of light in the entire observable universe accounts for less than 5% of what is actually out there. 5%. That means 95% of everything that exists, everything that has mass, everything that exerts gravity, everything that shaped the structure of the cosmos from the very beginning, is something we have never directly seen, never touched, never captured in a detector, and never fully understood. We have a name for most of it. We call it dark matter and dark energy. But having a name for something is not the same as understanding it. Sometimes a name is just a placeholder for a question we don't know how to answer yet. This documentary is about that question. About the long, strange, deeply human journey toward understanding what the universe is actually made of. About the astronomers and physicists who noticed one by one that something was wrong, that the cosmos was behaving in ways that the visible world simply could not explain. About the evidence that built, slowly and then overwhelmingly, into one of the most profound discoveries in the history of science, and about the extraordinary fact that we still, despite everything we know, cannot say with certainty what dark matter actually is. We have been staring at the universe for thousands of years. We have mapped it, measured it, sent probes through it, pointed our most powerful telescopes into its farthest corners, and still, the majority of what is out there remains beyond our grasp. That is either the most humbling fact in science or the most exciting one. Perhaps it is both. Let us begin. The first thing you need to understand is that the universe is not what it looks like. This is not a metaphor. It is a literal statement about physics. When we look at a galaxy, a real galaxy, not an artist's impression, but the actual telescopic image of 100 billion stars rotating around a common center, we are looking at something that is behaving in a way that defies our understanding of gravity. The stars at the edges of that galaxy are moving far too fast. They should, by all rights, have flown apart long ago. The gravity of the visible matter alone is nowhere near sufficient to hold them in place. And yet there they are, spinning, stable, graceful, as though held by something we cannot see. This is the central mystery. This is the question that sits beneath everything we are going to explore. Not just what dark matter is, but what it means that something so vast, so influential, so fundamental to the existence of galaxies and clusters and cosmic structure could be completely invisible to every instrument we have ever built. The universe is telling us something. It has been telling us for decades. The signal is clear. The mass is there. We just cannot find what is producing it. And that silence, that absence of a signal where a signal should be, is, in its own strange way, one of the loudest things in science. So let us go back back to the beginning of this story, back to the moment when the first person noticed that something didn't quite add up. The year was 1933. The place, the California Institute of Technology in Pasadena. The man, Fritz Zwicky. Zwicky was not an easy person to get along with. He was brilliant, combative, frequently insulting to his colleagues, and possessed of a mind that operated at a pitch of intensity that made most people uncomfortable. He was also, by most accounts, almost always right, which made him even harder to deal with. At the time, Zwicky was studying a vast collection of galaxies known as the Coma Cluster, a cluster of over 1,000 galaxies located roughly 320 million light-years from Earth. He was interested in how fast those galaxies were moving relative to one another, and he used a well-established method, the Doppler shift. When a light source moves toward you, its light shifts toward the blue end of the spectrum. When it moves away, toward the red. By measuring those shifts, you can calculate velocity, standard physics, routine procedure. What was not routine was the answer he got. The galaxies in the Coma Cluster were moving far too fast, dramatically too fast. If you took all the luminous matter in the cluster, all the stars, all the gas, all the visible material, and calculated how much gravity it could exert, the galaxies should have been flying apart. The cluster, by every reasonable calculation, should not exist. But it did exist. It was right there. 1,000 galaxies bound together, clearly not flying apart. Zwicky concluded that there had to be additional mass that wasn't visible. He called it Dunkel Materie, dark matter, a placeholder term for something missing from the equation. He published his findings. He was largely ignored. This is one of the recurring themes in the history of science. The first person who sees something correctly often sees it too early. The world has not yet accumulated enough context to appreciate what they're saying, and so the observation gets filed away, noted but not acted upon, a curiosity rather than a crisis. Dark matter would remain a curiosity for another 4 decades. Meanwhile, astronomy was advancing rapidly. Telescopes were becoming more powerful, where spectroscopy, the analysis of light, was becoming more sophisticated. Astronomers were learning to read the cosmos in new ways, through radio waves, through infrared, through X-rays. The universe was becoming more legible, and the more legible it became, the stranger it looked. By the 1960s, astronomers had turned their attention to a fundamental question. How do galaxies rotate? Not whether they rotate, that was well known, but how the rotation speed varies across the structure of a galaxy. Theory had a clear prediction. In our solar system, planets closer to the Sun move faster, and planets farther out move more slowly. Mercury races around at nearly 50 kilometers per second. Neptune plods along at just over 5. The reason is simple. Most of the mass is concentrated at the center, in the Sun, and gravity weakens with distance. The farther you are from the mass, the slower you orbit. This is called Keplerian rotation, after the astronomer Johannes Kepler. And it was entirely reasonable to expect galaxies to behave the same way. Yet most of the mass, most of the stars, should be concentrated toward the center. So stars near the center should orbit quickly, and stars at the edges should orbit slowly. What astronomers actually observed was something else entirely. In the late 1960s and early 1970s, an astronomer named Vera Rubin working at the Carnegie Institution in Washington, began a systematic study of galaxy rotation. She was working with her colleague Kent Ford, who had built a particularly sensitive spectrograph, an instrument for analyzing the light from different parts of a galaxy and measuring their velocities. Together, they began studying the Andromeda Galaxy, then other spiral galaxies, one after another. The results were consistent, deeply, persistently, disturbingly consistent. The rotation curves were flat, where theory predicted a graceful decline, fast at the center, slow at the edges. The observed velocities barely changed at all. Stars at the outermost edges of galaxies were moving just as fast as stars much closer to the center. In some cases, only the curves were so flat that the outer stars appeared to be moving slightly faster. This was impossible if the only mass in the galaxy was the visible matter. The outer stars should be flying off into the void. The fact that they were not, the fact that galaxies were coherent, rotating structures, demanded an explanation. Rubin's conclusion, stated carefully and supported by data from dozens of galaxies, was that the luminous matter we can see accounts for only a fraction of the actual mass. There had to be a vast halo of invisible material surrounding every spiral galaxy. A halo that was not emitting light, not absorbing light, not interacting with light in any way that made it detectable, but exerting gravity, enormous amounts of gravity. This was not a minor correction to the models, it was a revolution. The galaxies we can see are, in a sense, just the visible cause of something far larger, something we cannot perceive directly. Every galaxy is embedded in a dark matter halo that may extend to 10 or 20 times the visible radius. The visible part, the beautiful spiral arms, the glowing center, the arcing trails of stars, is like the lit portion of a much larger, much more massive invisible structure. When Rubin published these findings through the 1970s, the reception was slow and skeptical. Some astronomers suggested measurement errors. Others proposed alternative explanations, but the data was solid. And as more groups confirmed the results, and as the pattern repeated across galaxy after galaxy, the skepticism began to give way. By the 1980s, the scientific consensus had quietly, firmly shifted. Dark matter was no longer a curiosity. It was a fixture of the standard model of cosmology. Vera Rubin would go on to study hundreds of galaxies over her long career. She never wavered in her interpretation, and though she was never awarded the Nobel Prize, a subject that remains a painful point of contention in the scientific community, given the magnitude of her discovery. Her work stands as one of the foundational pillars of modern astrophysics. She died in 2016. The mystery she helped define remains unsolved. By now you might be wondering, how certain are we? Is the rotation of galaxies the only evidence for dark matter? Could there be some other explanation? Some modification to the laws of gravity that makes things look wrong without anything actually being missing? These are exactly the right questions, and the answer to the first one is, the evidence is overwhelming, and it comes from multiple independent directions. Dark matter is not a theory built on a single observation. It is a conclusion supported by at least 5 distinct and mutually reinforcing lines of evidence, each developed independently, each pointing to the same general conclusion. The first, as we've seen, is galaxy rotation curves. The second is the behavior of galaxy clusters. The same discrepancies Zwicky noticed in 1933, now confirmed and quantified across hundreds of clusters to a very high degree of precision. The visible mass of galaxy clusters, even when you include all the hot gas that fills the space between galaxies, and which is actually more massive than the galaxies themselves, is simply not enough to explain why clusters hold together. Something else is there. The third line of evidence is gravitational lensing. This is one of the most beautiful and direct demonstrations of dark matter's existence, and it deserves some attention. Einstein's theory of general relativity tells us that mass warps space-time, and when space-time is warped, light bends as it travels through it. A very massive object, a galaxy, be it a cluster of galaxies, acts as a gravitational lens. It bends and distorts the light from objects behind it, creating arcs, rings, and multiple images where there is only one real source. By measuring how strongly a cluster bends light, you can calculate its total mass. And when astronomers do this calculation, the answer they get is consistently far larger than the mass of the visible matter. The difference is attributed to dark matter. One of the most striking demonstrations of this came in 2006 from a system called the Bullet Cluster. This is actually two galaxy clusters that have passed through each other, a cosmic collision of almost incomprehensible violence. As they passed, the hot gas in each cluster, which makes up most of the ordinary matter, slowed down due to electromagnetic interactions and piled up in the middle. But the dark matter halos of the two clusters passed straight through each other, barely interacting at all, and continued in the original direction of travel. The result is a cluster in which the visible matter, the gas mapped in X-rays, is in a different location from the gravitational mass, inferred from lensing. The mass is where the galaxies are. The gas is in between. The two have separated. This is not a subtle effect. It is visually clear in the combined maps of X-ray emission and gravitational lensing, and it is extraordinarily hard to explain without dark matter. If there were no dark matter and gravity worked differently, the gas, which carries most of the ordinary mass, would be where the gravitational center should be. Instead, the lensing maps show that the gravity follows the galaxies. Something is traveling with the galaxies that is not the gas. The Bullet Cluster remains one of the most compelling single pieces of observational evidence that dark matter is real, that it is distinct from ordinary matter, and that it does not interact electromagnetically, meaning it neither emits nor absorbs light, and it is not subject to the pressure forces that slow down the gas. The fourth line of evidence takes us much farther back in time, to the very early universe. The cosmic microwave background, the CMB, is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this, the universe was a plasma, opaque, with light trapped. After this moment, the photons were freed. They have been travelling ever since, and we can detect them today, uniformly spread across the entire sky, with a temperature of just under 3 degrees Kelvin. This CMB is not perfectly uniform. It has tiny fluctuations, temperature variations of about 1 part in 100,000, that encode information about the early universe. These fluctuations are the seeds from which all cosmic structure grew. The pattern of those fluctuations measured with extraordinary precision by satellites like WMAP and Planck, contains information about the relative amounts of different types of matter and energy in the universe. When cosmologists analyze this pattern, they find that it is best explained by a model in which roughly 5% of the universe is ordinary matter, roughly 27% is dark matter, and roughly 68% is dark energy, a mysterious phenomenon associated with the accelerating expansion of the universe. The dark matter and dark energy percentages are not pulled out of thin air. They are fitted to the CMB data, and that fit is extraordinarily good. This is important. The CMB analysis and the galaxy rotation curves are completely independent lines of evidence. One uses the behavior of spinning galaxies, the other uses the pattern of the oldest light in the universe, and they agree. They agree on the existence of dark matter, and they broadly agree on how much of it there is. And the fifth line of evidence is the large-scale structure of the universe itself. When you map the distribution of galaxies across enormous volumes of space, you find that they are not randomly distributed. They form a vast, intricate structure, a cosmic web of filaments, sheets, and nodes, with enormous voids between them. The filaments are hundreds of millions of light years long. The voids are hundreds of millions of light years across. The whole thing looks, in 3 dimensions, like a foam, or a neural network, or the inside of a sponge of breathtaking scale. Computer simulations that include only ordinary matter cannot reproduce this structure, but simulations that include dark matter, with its specific properties, do reproduce it in remarkable detail. The cosmic web forms because dark matter provides the gravitational scaffolding. It clumps first, creating potential wells into which ordinary matter flows. Galaxies form inside those wells. Filaments form along the connections between wells. Without dark matter, the universe would look nothing like what it does. There would be no cosmic web. There might be no galaxies at all, or at least not galaxies as we know them. The structure of everything we see is a consequence of the structure of something we cannot see. Take a moment to sit with that. The cosmic web, that vast intricate architecture of filaments and voids stretching across the observable universe, is fundamentally a dark matter structure. The ordinary matter, the stuff we're made of, the stars and gas and planets and everything you have ever touched or seen or breathed. This ordinary matter is a passenger. It flows into the gravitational valleys carved by dark matter. It congregates where dark matter has already clustered. It lights up the nodes and filaments of a framework that was, and still is, invisible. We are not the primary ingredient of the universe. We are something that formed in the pockets of something else. This is a conceptual shift of the first order. In the history of ideas about our place in the cosmos, we have been displaced many times. From the center of the solar system to a planet orbiting the sun. From the center of the galaxy to an unremarkable position on one of its outer arms. From the galaxy being the universe to the galaxy being one of hundreds of billions. But the idea that ordinary matter, the entire category of substance that everything we have ever known belongs to, is a minor constituent, a late arriving trace element in a cosmos shaped by something entirely different, that is a displacement of a different kind. It is not a displacement in space, it is a displacement in substance. Let us look a little more closely at how this scaffolding works. When the universe was young, Very young, in the first few 100 million years, it was nearly uniform. The distribution of matter was almost perfectly smooth. Almost. There were tiny variations, quantum fluctuations from the earliest moments, imprinted on the fabric of space. These tiny variations were the seeds. Dark matter began to cluster around those seeds almost immediately. Ordinary matter, at this point, was still coupled to radiation. It was interacting so frequently with photons that it couldn't easily collapse under gravity. Dark matter, not interacting with radiation at all, was free to clump. It fell into its own potential wells and began to form halos. When ordinary matter finally decoupled from radiation, at that moment we already described when the CMB was released, it found a universe that dark matter had already begun to organize. The dark matter halos were there, waiting. Ordinary matter fell into them. Gas cooled, condensed, formed the first stars. The first stars formed the first galaxies. Galaxies clustered along the filaments of the dark matter web. The whole story of cosmic structure, from the first stars to the present-day cluster of galaxies that contains our own Milky Way, begins with dark matter. Dark matter did not just contribute to structure, it made structure possible. And here is something worth pausing on. If dark matter did not exist, or if it had slightly different properties, we would not be here. The galaxies that allowed heavy elements to form and spread, the solar systems that allowed rocky planets to exist, the conditions that allowed life to arise. All of this follows in a causal chain from the gravitational behavior of dark matter in the early universe. We are children of the invisible. Having established that dark matter almost certainly exists, and having traced the web of evidence that points to its existence, we arrive at a question that is both more specific and more frustrating. What is dark matter made of? Before we get to what it might be, it helps to establish what it is not, because the history of dark matter research has been, in part, a history of elimination, of ruling things out, one by one. The first thing dark matter is not is ordinary matter in a dark form. This might seem like an obvious solution at first. After all, there are lots of objects in the universe that do not emit much light. Dead stars, brown dwarfs, rogue planets, black holes. Collectively, these were called MACHOs, an acronym for Massive Compact Halo Objects. For a while, they seemed like a plausible candidate. The problem is accounting. Ordinary matter, including all of the dim and dark forms of it, is made of protons and neutrons. Cosmologists call these particles baryons. The physics of the early universe, specifically the period called Big Bang nucleosyntheses, when the lightest elements were forged in the first few minutes after the Big Bang, constrains very precisely how much baryonic matter could have been created. The answer is consistent with what we observe in the cosmic microwave background. Ordinary matter is about 5% of the universe's content. Dark matter is about 27%. You simply cannot make 27% of the universe out of baryons. The physics doesn't allow it. This is one of the most important points in the entire dark matter story. Dark matter is not ordinary matter hiding in the dark. Or it is not dim stars or cold gas clouds or black holes formed from normal stellar evolution. It is something genuinely different. Something that does not belong to the category of matter we know. It is a new kind of substance, non-baryonic, not made of protons or neutrons. something that the standard model of particle physics as it currently stands does not account for. Microlensing surveys, observations that monitor millions of stars for the brief brightening that occurs when a compact massive object passes in front of them, have confirmed this. Machos exist, but there are far too few of them to account for the dark matter. They are not the answer. Dark matter is also not the result of errors in our understanding of gravity. This has been proposed seriously and rigorously in an alternative theoretical framework called Modified Newtonian Dynamics, or MOND. Proposed by physicist Mordechai Milgrom in 1983, MOND suggests that gravity behaves differently at very low accelerations than Newton's law predicts. If gravity were slightly stronger at low accelerations, you might be able to explain the flat rotation curves of galaxies without invoking dark matter at all. MOND is a genuinely interesting idea, and it has had notable successes. It does well at predicting the rotation curves of individual galaxies, sometimes remarkably well. And Milgrom's insight that there is an empirical relationship between the surface density of stars in a galaxy and the acceleration at which dark matter seems to become necessary is real. It is called the radial acceleration relation, and it is one of the genuinely puzzling aspects of the dark matter picture. But MOND has serious problems when you try to extend it beyond individual galaxies. It struggles to explain galaxy clusters. It cannot naturally reproduce the cosmic microwave background fluctuations, and the bullet cluster, where the gravitational mass and the visible matter are in different places, is very hard to accommodate in any purely modified gravity theory without adding something extra. More sophisticated relativistic extensions of MOND have been proposed, most notably by Jacob Bekenstein in a theory called TVES, tensor vector scalar gravity. These are mathematically sophisticated and deserve serious consideration, but they have not displaced the dark matter paradigm. They remain alternatives that most, though not all, cosmologists find less compelling than the evidence for actual dark matter particles. What the MOND story teaches us, though, is something important. The relationship between dark matter and gravity is deeply intriguing. The radial acceleration relation, the fact that how much dark matter you seem to need in a galaxy, correlates with the distribution of the visible matter, is not something that the standard dark matter picture explains with any elegance. This is an active area of debate, and it suggests that whatever dark matter is, it may have some kind of deeper connection to ordinary matter than a simple coexistence would imply. If dark matter is not ordinary matter and not modified gravity, then it must be a new kind of particle, or perhaps several new kinds of particles. Over the past several decades, theorists and experimentalists have proposed and pursued a range of candidates. Some have fallen by the wayside. Others remain very much alive. The most well-studied and most heavily pursued candidate is a class of particles known as WIMPs, weakly interacting massive particles. The name tells you most of what you need to know. They are massive, somewhere between 10 and a few thousand times the mass of a proton, and they interact weakly, not in the colloquial sense, but in the technical sense. They feel the weak nuclear force, one of the four fundamental forces, but not the electromagnetic force. This means they do not interact with light. They do not emit it, absorb it, or scatter it. They are, in the most literal sense, dark. The WIMP hypothesis has a beautiful feature that physicists call the WIMP miracle. If you calculate how many WIMPs would have been produced in the early universe and then survived as it cooled using standard particle physics, the number you get is remarkably close to the amount of dark matter we observe today. This coincidence is striking. It suggests that WIMPs naturally arrive at the right abundance, without any fine-tuning, just from the basic physics of the hot early universe. This is the kind of result that physicists find deeply seductive. WIMPs are also theoretically motivated by problems that have nothing to do with dark matter. In particular, they appear naturally in a class of theories called supersymmetry, which proposes that every known particle has a superpartner with different spin properties. The lightest supersymmetric particle, often called the neutralino, would be stable, heavy, and weakly interacting. In other words, a WIMP. Supersymmetry has its own theoretical motivations related to solving problems in the Higgs sector of the Standard Model. The fact that it also predicts a natural dark matter candidate was seen, for a long time, as a powerful endorsement of both ideas simultaneously. The hunt for WIMPs has been one of the great scientific enterprises of the past 3 decades. It has taken 3 main forms: underground detectors, where you bury a tank of extremely pure material deep underground, under kilometers of rock, and wait for a WIMP to scatter off a nucleus. Particle accelerators, where you try to produce WIMPs by smashing particles together with enough energy. And indirect detection experiments, where you look for the products of WIMPs annihilating each other in places where they are dense, like the galactic center or nearby dwarf galaxies. None of these approaches has, as of yet, produced a confirmed detection. The underground experiments have grown progressively more sensitive. The Lux Zeppelin detector in South Dakota, sitting nearly 1,500 meters underground in an old gold mine, is now sensitive to interactions so rare that a particle could pass through a light year of lead with only a 50% chance of interacting, and still no signal. The Large Hadron Collider at CERN has explored vast regions of supersymmetric parameter space and found nothing. Indirect detection experiments have produced hints and anomalies that have, one by one, been attributed to other sources. This is a crisis of a kind. Not a crisis in the sense that dark matter is in doubt. The evidence for its existence is as strong as ever. But a crisis in the sense that the leading candidate has been pushed into increasingly uncomfortable corners of theoretical space. The most natural WIMP masses and interaction cross-sections have been ruled out. The hypothesis is not dead, but it is under significant pressure, and so physicists have been exploring other candidates with renewed seriousness. One of the most interesting alternatives is the axion. Axions are hypothetical particles that were originally proposed for a completely different reason: to solve a problem in quantum chromodynamics, QCD, the theory that describes how quarks and gluons interact. The problem, known as the strong CP problem, concerns why the strong nuclear force does not seem to violate charge parity symmetry, even though the theory permits it to. A proposed solution, developed by Frank Wilczek and Steven Weinberg in 1977, based on earlier work by Roberta Peccei and Helen Quinn, involves introducing a new field whose quantum is the axion. What makes axions interesting as dark matter candidates is that they would be produced in large quantities in the early universe. They would be extremely light, far lighter than WIMPs, near possibly by many orders of magnitude, and they would interact with ordinary matter only extremely weakly. This combination of lightness and abundance could produce the right density of dark matter. Because axions are so light, detecting them requires completely different methods than WIMP experiments. One approach is to look for the conversion of axions into photons in a strong magnetic field. This is the principle behind the ADMX experiment, the Axion Dark Matter experiment, running in the United States. Others use resonant microwave cavities designed to amplify the photon signal from axion conversion. The search for axions is ongoing, and it represents one of the most active frontiers in dark matter research. Unlike WIMPs, the axion hypothesis has not been significantly constrained by experiment, partly because the relevant parameter space is so vast, and partly because the experimental technology to probe it has only recently reached the required sensitivity. Another candidate that has attracted substantial attention is the sterile neutrino. We know that ordinary neutrinos exist. They are real particles, produced in enormous quantities in the Sun and in nuclear reactions, and they pass through matter almost entirely without interaction. But ordinary neutrinos are very light, and they move at nearly the speed of light, making them hot, dark matter that would have washed out the fine-scale structure of the early universe. The observations of the cosmic web tell us that dark matter must be cold, slow-moving at the time of galaxy formation. Sterile neutrinos are hypothetical heavy cousins of the ordinary neutrino. They would interact with ordinary matter only through a very weak mixing with the normal neutrino states. If they have the right mass, in the range of kilo-electron volts to mega-electron volts, they could be cold enough to be consistent with structure formation, and they could be produced in the early universe at approximately the right abundance. There are also some intriguing X-ray signals from galaxy clusters, most notably a line at 3.5 kilo-electron volts detected in multiple datasets, that have been proposed as potential signatures of sterile neutrino decay. This remains unconfirmed and controversial, but it is one of the most tantalizing hints in the field. The candidate zoo does not stop there. Primordial black holes formed directly from density fluctuations in the very early universe, before any stars existed, have enjoyed a resurgence of interest, partly driven by the detection of gravitational waves from black hole mergers by the LIGO collaboration beginning in 2015. Could dark matter be, in part, a population of these ancient black holes? The possibility has not been ruled out for certain mass ranges, though strong constraints exist across much of the parameter space. There are also more exotic proposals: ultralight scalar fields, fuzzy dark matter with quantum wavelengths the size of entire galaxies, dark photons, self-interacting dark matter, and theories in which dark matter interacts with itself through forces that have no connection to any of the four known fundamental forces. The breadth of these proposals is itself significant. It reflects the fact that we have no direct observational handle on the particle properties of dark matter. We know what it does gravitationally. We know, from the bullet cluster and other observations, that it does not interact electromagnetically. We know, from structure formation, that it must be cold. Beyond that, we are theorizing in the dark, perhaps an appropriate metaphor, guided by the internal logic of physics, by the elegance of particular solutions, and by whatever hints the experiments can provide. The search for dark matter is one of the great scientific endeavors of our era. It spans continents, disciplines, and scales of physical phenomenon that are hard to hold in the mind simultaneously. Deep underground, in mines and tunnels around the world, physicists have built some of the most sensitive detectors ever made. The goal is to catch a dark matter particle in the act of colliding with an ordinary nucleus. The signal would be small, a tiny amount of energy deposited in the detector. The challenge is that the background noise, from cosmic rays, from natural radioactivity in the rock, from trace impurities in the detector itself, is also very small, and distinguishing a genuine signal from noise requires extraordinary care and extraordinary patience. The Lux-Zeppelin experiment, known as LZ, contains 10 tons of liquid xenon. He's chilled to a temperature just above the boiling point of liquid nitrogen. When a particle collides with the xenon nucleus, it produces a small flash of light and a small cloud of electrons. By measuring both signals precisely, physicists can determine the energy of the collision, the type of particle involved, and, crucially, whether the interaction looks more like a known background particle or something potentially exotic. LZ is located 1,478 meters underground in the Sanford Underground Research Facility in South Dakota, built in the historic Homestake Gold Mine. The depth is not arbitrary. 2 kilometers of rock overhead absorbs most of the cosmic ray muons that would otherwise flood the detector with fake signals. Even so, the experiment requires active shielding systems, careful selection of construction materials for their extreme radiological purity, and sophisticated analysis algorithms to separate signal from noise. Similar experiments are running in Italy's Gran Sasso laboratory under the Apennine Mountains and in the Jinping Underground Laboratory in China, one of the deepest in the world. These laboratories have turned the ancient crust of the Earth into a scientific instrument. At the other end of the scale spectrum, the Large Hadron Collider at CERN near Geneva has been searching for dark matter through a different approach, creation rather than detection. If you smash protons together with enough energy, you might produce dark matter particles directly. You would not see them. By definition, dark matter does not interact with your detector, but you would see the recoil. You would see events in which a lot of momentum appears to be missing, carried away by invisible particles. This is called the missing energy signature, and it is one of the primary search strategies at the LHC. So far, no convincing missing energy signal has emerged that cannot be explained by known physics, specifically by the neutrinos that are already well understood. The LHC has also failed to find evidence for supersymmetry, the theoretical framework that so naturally provides a WIMP candidate. This has led to considerable soul-searching in the particle physics community. There is also indirect detection, looking not for dark matter directly, but for the products of dark matter interactions or annihilations in regions where dark matter is dense. The galactic center, for example, is expected to be a dark matter spike, a region of very high dark matter density, where annihilation events should produce gamma rays, neutrinos, or antimatter. The Fermi Gamma Ray Space Telescope has mapped the gamma ray sky with remarkable precision, and there are anomalies in the galactic center that have attracted attention. But interpreting these signals is extremely difficult. The galactic center is also one of the most complex astrophysical environments in the universe, full of pulsars, supernova remnants, and other energetic phenomena. Distinguishing a dark matter signal from astrophysical background is a formidable challenge. Cosmic ray experiments like Pamela and AMS-02, which flew on the International Space Station, have measured the spectrum of cosmic ray positrons and antiprotons with extraordinary precision. There were hints a decade ago of an excess of positrons at high energies that some interpreted as possible dark matter annihilation. Subsequent work has attributed much of this excess to astrophysical sources, particularly pulsars. But the debate continues. Gravitational wave observatories, LIGO, Virgo, and the future space-based LISA detector have opened a completely new window on the universe. They are sensitive not to electromagnetic radiation, but to ripples in space-time itself. If dark matter includes a component of compact objects, primordial black holes, or exotic dense objects, gravitational wave observations might eventually reveal it through the statistical distribution of merger events or through specific signatures that ordinary stellar mass black holes would not produce, and neutrino telescopes, like IceCube at the South Pole, a cubic kilometre of Antarctic ice instrumented with thousands of sensitive detectors, are searching for the high-energy neutrinos that some dark matter models predict would be produced when dark matter particles annihilate in the core of the Earth or the Sun. No convincing signal has emerged there either. The sheer diversity of these experiments speaks to both the seriousness with which the scientific community takes dark matter and the depth of our ignorance about its nature. We are searching everywhere with every tool at our disposal, and we have not found it. This is not a failure. It is science working exactly as it should, systematically eliminating possibilities, narrowing the parameter space, and building the case for wherever the truth actually lies. But it is also honest to acknowledge the frustration. Each null result, each experiment that comes up empty, is information. But it is not the information we were hoping for. The absence of a WIMP detection has done something interesting to the field of dark matter research. It has opened it up. For much of the 1990s and early 2000s, the theoretical community operated with a certain confidence. WIMPs were the expected answer. Supersymmetry was widely anticipated to reveal itself at the LHC. The detection of dark matter seemed like a matter of when, not whether. Experiments were designed specifically to explore the WIMP parameter space that theory most strongly favoured. Now, the landscape is different. The favoured WIMP mass range has been probed and largely excluded. Supersymmetry has not appeared. The LHC saw the Higgs boson, a brilliant vindication of the standard models, but nothing beyond it. And this has produced a kind of creative disruption in the field. Any new ideas are being entertained that might have seemed less urgent when the leading candidate looked so promising. There is, for example, a growing community of physicists interested in dark sector models, theories in which dark matter is not a single particle, but a whole suite of particles interacting with each other through forces that are entirely separate from the four forces we know. A dark photon, a dark nucleus, a dark atom. In these models, dark matter may have a rich internal structure that we have been missing because we were looking for something simpler. Self-interacting dark matter, a model in which dark matter particles can collide with each other, as well as with ordinary matter, has attracted attention because of some apparent tensions between the predictions of cold dark matter models and observations of small-scale structure. The standard cold dark matter model predicts that galaxies should have cuspy density profiles, rising steeply toward the center. But many dwarf galaxies appear to have chord profiles, flatter at the center. Similarly, simulations predict more small satellite galaxies around the Milky Way than we observe. These are known as the cusp core problem and the missing satellites problem. These discrepancies are genuinely puzzling, and they have driven a significant research program into whether they reflect new physics, either in the nature of dark matter or in the effects of ordinary matter processes like supernova feedback, or whether they are artifacts of simulation techniques. The tension between observation and simulation at small scales does not by itself overturn the dark matter picture, but it does suggest that we may be missing something about dark matter's properties. Cold, collisionless dark matter is the simplest version of the idea, but simplest is not always right. There is also the deeper philosophical tension embedded in the MOND versus dark matter debate. Milgram's original observation, that there is a characteristic acceleration scale below which galaxies seem to need dark matter, is real, and it is still not fully explained by the standard dark matter model. In the standard picture, the tightness of the radial acceleration relation is attributed to feedback processes, gas dynamics, star formation, stellar winds. But the origin of the characteristic acceleration scale, which happens to be related to the cosmological constant, one of the most mysterious quantities in physics, remains unexplained. There are theorists who take this seriously and who are developing frameworks that try to bridge the MOND phenomenology with the particle physics approach. These are not mainstream, but they represent a genuine scientific effort to reconcile two sets of observations that do not sit entirely comfortably together. The honest answer is that we do not know what dark matter is, and we do not know whether the standard cold dark matter paradigm is correct in all its details. What we know is that something is out there, that it has mass, that it shaped the cosmos, and that it is not ordinary matter. The details, the identity of the particle, and the microphysics of its interactions, the full picture of small-scale structure, remain open. And that openness is where the most interesting work is happening. Before we move toward the deeper philosophical questions, it is worth pausing to clarify something that is often confused. Dark matter and dark energy are not the same thing. They are not even related as far as we know. They happen to share the word dark because both are invisible to us in the conventional sense. But they are almost certainly completely different phenomena. Dark matter, as we have discussed, has mass and gravity. It clusters, it forms halos and filaments. It played a crucial role in the formation of structure. It pulls things together. Dark energy is almost the opposite. It is the name we give to the phenomenon responsible for the accelerating expansion of the universe. In 1998, was two independent teams of astronomers studying distant Type 1a supernovae, which serve as standard candles because they always achieve roughly the same peak brightness, discovered that the universe is not merely expanding, it is expanding faster and faster over time. Something is pushing space apart, counteracting gravity on the larger scales. The simplest explanation for dark energy is that it is the energy of empty space, what Einstein called the cosmological constant. Even in a perfect vacuum, quantum mechanics tells us that space is not truly empty. It is filled with fluctuating quantum fields, and those fluctuations carry energy. This vacuum energy would cause space to expand. The problem is that when physicists calculate how much vacuum energy quantum field theory predicts, well, the answer is astronomically wrong, off by roughly 120 orders of magnitude from the observed value. This is sometimes called the worst prediction in the history of physics, and understanding why the cosmological constant has the tiny but non-zero value it does is one of the deepest unsolved problems in all of science. Dark energy makes up about 68% of the universe's total energy content. Dark matter accounts for about 27%. Ordinary matter, everything we have ever seen, every atom in every star, every molecule in every organism, every structure ever built by human hands, amounts to about 5%. 5%, held in a universe mostly composed of two things we fundamentally do not understand. This is the state of knowledge at the frontier of cosmology in the 21st century. Imagine the moment. Somewhere, in some underground laboratory, a signal appears in a detector that cannot be explained by any known background. A cluster of events at the right energy, with the right characteristics, repeating with statistical significance that grows over days, then weeks, then months. The analysis proceeds, careful and cautious. Alternative explanations are ruled out one by one. Other experiments are alerted and begin to look at the same region of parameter space. Confirmation comes, papers are written, peer review takes its course, and then the announcement, dark matter has been detected. What would that moment mean? On the most immediate level, it would mean we know what dark matter is. We would have a mass, an interaction cross-section, perhaps quantum numbers. We could build a consistent picture of where dark matter fits in the particle physics landscape. We could refine our cosmological models with a new degree of precision. We could better understand the formation and evolution of galaxies, the structure of the cosmic web, the early history of the universe. But the implications run deeper than that. If dark matter turns out to be a supersymmetric particle, it would be evidence for an entire doubling of the particle zoo, a vast new sector of reality that has been there all along, invisible and undetected. It would validate decades of theoretical work. It would open up an entire new domain of experimental physics. If it turns out to be an axion, it would simultaneously solve two deep problems in physics, the strong CP problem and the dark matter problem, with a single elegant particle. It would be one of the most powerful examples of theoretical parsimony in the history of physics. If it turns out to be something completely unexpected, a new type of particle with no connection to any existing theoretical framework, it would trigger a revolution in our understanding of particle physics. The standard model, which has described every known particle and interaction with extraordinary precision for 50 years, would be revealed as incomplete in a new and specific way. The challenge of building a better model would begin. Each of these outcomes would be one of the greatest scientific discoveries in human history. The detection of dark matter would rank alongside the discovery of the electron, the discovery of quantum mechanics, the discovery of the double helix, the detection of gravitational waves. It would be a genuine turning point. One of those moments when our picture of reality shifts fundamentally. And yet it is also possible that dark matter will not be found by a single decisive detection. It may be a gradual process, multiple experiments converging, statistical excesses that build slowly, theoretical frameworks refined through a combination of null results and positive hints. Perhaps we will know what dark matter is not, in increasingly precise detail, until the remaining space of possibilities collapses to a point. Science sometimes works this way, not in a single revelation, but in a slow narrowing of the unknown. There is also the possibility, uncomfortable but real, that we will not find dark matter particle candidates within the reach of any experiment we know how to build. Dark matter might exist at energy scales that are inaccessible to current or foreseeable technology. It might interact with ordinary matter at rates so low that no detector of reasonable size could accumulate a statistically meaningful number of events. In that case, we might never have direct evidence of what dark matter is made of. We would know it exists. We would know with high precision how much of it there is and how it behaves gravitationally. But its identity, the particle or particles from which it is composed, might remain forever beyond our grasp. This is not a comfortable thought, but science requires us to take it seriously. There is a broader lesson here, and it is one of the most important things that dark matter teaches us about the nature of knowledge itself. Throughout the history of science, we have repeatedly discovered that the world contains more than our senses can directly perceive. We cannot see atoms, but we deduce their existence from the behavior of gases and the patterns of chemical reactions. We cannot see electric fields, but we can measure their effects. We cannot see the curvature of space-time, but we can track the motion of light and matter through it. Science has always been, in part, the art of inferring the invisible from the visible. But dark matter pushes this further than we have gone before. It is not simply invisible in the sense that it requires an instrument to detect, like an atom or an electric field, which respond to electromagnetic probes. Dark matter is invisible in a more fundamental sense. It does not interact with electromagnetic radiation at all. It cannot be illuminated. It cannot be photographed. It cannot be observed with any instrument that relies on light, which is to say, almost every instrument we have ever built. Our entire scientific apparatus for observing the universe is built on the assumption that things interact with light. Telescopes collect light. Spectrographs analyze it. Cameras record it. Even many non-optical instruments, X-ray telescopes, radio arrays, infrared detectors, are detecting electromagnetic radiation of one form or another. Dark matter is fundamentally outside the reach of all of them. This is new territory, and it raises a question that is not merely scientific but philosophical. What are the limits of human knowledge? We have always assumed, perhaps without examining the assumption, that in principle everything that exists can be observed, that with the right instrument, at the right wavelength, with the right sensitivity, we can see anything. Dark matter challenges that assumption. It suggests that there may be vast aspects of reality, perhaps the majority of reality, that are in principle accessible only through their indirect effects on the things we can see. We are like people standing in a room, unable to see the walls, knowing they must be there because of the way sound echoes. We have never seen the walls, we have never touched them, but we can hear their existence in every reverberation, in every reflection of every sound. The walls are real, but our knowledge of them is and may always be indirect. This has implications for how we think about scientific knowledge itself. We often speak of understanding the universe. But what does understanding mean when we cannot perceive the majority of what is there? We have built remarkably accurate maps of the cosmos, maps of its structure, its history, its composition. But those maps are, in a significant sense, maps of the 5%. The other 95 is represented in those maps only as a mathematical necessity, as the gravity that the 5% requires to do what it does. There is a humility in this that I think is important. Not a humility that leads to despair or to the abandonment of scientific inquiry, but a humility that acknowledges the limits of our instruments, the specificity of our senses, the possibility that reality extends far beyond what we can, even in principle. I directly perceive the universe does not arrange itself for our convenience. It does not present itself in forms that our evolved senses can grasp. It simply is vast, complex, mostly invisible, mostly unknown, and we, these small, briefly living creatures on a rocky planet orbiting an ordinary star in an unremarkable galaxy, we have, through patience and ingenuity and the accumulated effort of generations, figured out just enough to know how much we don't understand. That is remarkable. It is genuinely deeply remarkable. We should not lose sight in all this cosmic scale of the human dimension of the story. Fritz Zwicky, who first named the problem, lived to see his insight marginalized and then vindicated. He was, by many accounts, Vera Rubin, by contrast, lived to see her work become foundational and celebrated, even if official recognition in the form of Nobel Prizes eluded her. She spoke often about the experience of being a woman in mid-20th century astronomy, a field that was, at the time, almost entirely male. She was refused access to certain telescopes. Her presentations were sometimes dismissed or ignored in ways that her male colleagues' work was not. She persisted. With a combination of careful observation and quiet determination that ultimately proved unanswerable, she also said something beautiful about the nature of her work. Late in her life, she remarked that she had no regrets about the mystery remaining unsolved. She had spent her career showing that the universe is vastly larger than we thought, vastly more complex, and vastly more interesting. That the question had not been answered, that it was still there, waiting, seemed to her not a failure but an invitation that she passed on to younger generations of astronomers and physicists who are still today pursuing it. There is something moving about that, about the way scientific knowledge is built across generations. The person who asks the question rarely lives to see the answer. Zwicky asked the question about the coma cluster. Rubin sharpened it into something that could not be ignored. Generations of experimentalists and theorists have been chasing the answer ever since, and the answer has not yet arrived. This is the normal tempo of the deepest questions. The universe is patient. The questions have been forming since the first stars ignited. We have only been looking carefully for a few decades. We should not expect to understand everything quickly. And there is something else worth saying. The people working on dark matter today, the graduate students staying late in university offices, developing new analysis techniques, the engineers at underground labs, maintaining equipment in conditions of extraordinary care, the theorists filling whiteboards with equations that may describe something no one has ever seen. These people are doing something extraordinary. They are extending the reach of human knowledge into territory that our ancestors could not have imagined. They are asking questions about the nature of reality that Aristotle, Newton, even Einstein did not have the tools to formulate. The work is hard. The answers are slow in coming. The field is full of false starts and disappointed hypotheses. But it continues. It always continues. because the question is there. And we are the kind of creatures who cannot leave a question alone. We arrive now at something that lives at the edge of science and philosophy, something that the dark matter problem makes unavoidable. What is reality made of? This question has been asked in many forms, across many centuries. The ancient Greeks asked it, Descartes asked it, Kant asked it. Physicists have been asking it, in increasingly precise mathematical terms, for the past 100 years. And we have learned extraordinary things. We know that matter is made of atoms, and atoms of protons, neutrons and electrons, and protons and neutrons of quarks, all held together by forces mediated by particles. We know that light is electromagnetic radiation, a wave in the quantum field of electromagnetism. We know that space-time is not a fixed background but a dynamic geometry that is shaped by energy and mass. But dark matter says all of that knowledge is knowledge of a small fraction of what exists. It says that the particle physics we know, the standard model that describes every particle and force we have ever detected, the model that has been tested to extraordinary precision in the most sensitive experiments ever built, this model is incomplete. It does not account for the majority of the matter in the universe. It describes a kind of universe in which there are only quarks and leptons and gauge bosons and the Higgs. And the universe we actually live in has, in addition to all of that, a large amount of something else. The nature of that something else is unknown, but its existence is certain, and the certainty of its existence alongside the uncertainty of its nature creates a peculiar epistemic situation. We know that reality contains something we don't understand, not tentatively, not as a working hypothesis, as one of the most well-supported conclusions in modern physics. We live in an incompletely understood universe, not because we haven't looked hard enough or thought carefully enough, but because the universe is, in a fundamental sense, larger than our current best theory. That gap between what we know and what is real is not a small one. It is not a rounding error. It is the dominant component of matter in the cosmos. This should give us pause, not just about dark matter, but about the nature of scientific knowledge in general. Our theories are not pictures of reality. They are maps of the portions of reality that are accessible to our instruments and methods. The map has been extraordinarily useful. It has built our technologies, healed our illnesses, sent spacecraft to the edges of the solar system and beyond. But it is not the territory. It has never been the territory. And dark matter is the proof. The philosopher and physicist might disagree about what exactly this means. A strict instrumentalist might say, so what? Our theories work within the domain they were designed to cover. The existence of dark matter is simply a reminder that there are domains they weren't designed for. A scientific realist might find this deeply significant, a challenge to the idea that our best theories give us genuine knowledge of the structure of nature. A pragmatist might simply say, let's go find out what it is and worry about the epistemology later. All of these responses are reasonable, but none of them diminishes the strangeness of the situation. We are here. We are made of ordinary matter. We are surrounded, permeated in fact, by dark matter, which passes through us and through the earth without the slightest interaction. Right now, every second, tens of thousands of dark matter particles pass through your body. They go straight through, barely interacting with a single atom, and continue on their way, indifferent to your existence. You're swimming in it. You have always been swimming in it, and you will never feel it. The search for dark matter is not slowing down. If anything, it is accelerating, driven by new experimental techniques, new theoretical frameworks, and a scientific community that has processed the disappointment of the WIMP null results and found in that disappointment a renewed creativity. The next generation of underground detectors will push sensitivity by another order of magnitude. LZ and its contemporaries will be followed by even larger, even cleaner experiments. At some point, the detectors will become large enough that they will inevitably encounter a fundamental background that is irreducible, the flux of neutrinos from the sun and from cosmic ray interactions in the atmosphere. This is known as the neutrino flaw, and it will set an ultimate limit on the sensitivity of direct detection experiments for WIMPs. If dark matter particles interact with ordinary matter at rates below this flaw, direct detection will not find them. At that point, the search strategy will have to shift. New approaches, more targeted to specific dark matter models, will become the primary tools. Axion experiments will cover parameter space that is currently inaccessible. Gravitational wave detectors will probe primordial black holes. CMB experiments and galaxy surveys will map the large-scale structure of the universe with unprecedented precision, constraining dark matter properties from the outside in. The Vera Rubin Observatory, named in honor of the astronomer whose work has been so central to this story, will image billions of galaxies, mapping the cosmic web in extraordinary detail and measuring the distribution of dark matter through gravitational lensing with unprecedented statistical power. The European Space Agency's Euclid satellite, launched in 2023, is doing something similar from space. These surveys will not detect dark matter particles, but they will constrain the models that describe how dark matter behaves on large scales, gradually closing off the theoretical options. In particle physics, the next generation of colliders, including proposals for a future circular collider at CERN with energies many times higher than the LHC, may probe energy scales where new particles could be produced. If dark matter is connected to physics at higher energy scales, these machines might reveal it. If it is not, if dark matter is genuinely disconnected from the energy range accessible to colliders, we will need another path. There is also the possibility of discovery from an entirely unexpected direction. And science has a long history of surprises, of discoveries that came not from the planned program, but from an anomaly noticed in a data set, a coincidence that turned out to be deeper than it appeared, a question asked by someone who was not supposed to be asking it. Dark matter might be discovered by an experiment that was built for something else entirely. It might be found in a data set that someone is currently analyzing for a completely different purpose. We simply do not know. What we do know is that the question is real. The universe is telling us something. In the rotation of galaxies, in the structure of galaxy clusters, in the pattern of the cosmic microwave background, in the architecture of the cosmic web, the universe is telling us that it is larger and more complex and more surprising than our current theories account for. The evidence is clear. The signal is unambiguous. We just haven't found the source. I want to step back toward the end of this long journey and say something about what it means to live at this moment in the history of science. We are alive in a period when the largest unsolved problem in physics is not something technical or mathematical. some algebraic knot that needs untangling. It is something existential. We do not know what most of the universe is made of, not even approximately, not within an order of magnitude. We do not know if dark matter is one thing or many things. We do not know if it has any internal structure. We do not know if it can decay, if it can self-annihilate, if it interacts with itself. We do not know if there is a dark sector with its own forces and particles. We do not know if dark matter and dark energy are connected. We do not know if modified gravity plays a role, or we do not know if the correct theory of dark matter will look anything like any of the candidates we have proposed. We are, in cosmological terms, in the equivalent of the mid-19th century, before the periodic table, before quantum mechanics, before the nuclear model of the atom. We know that elements exist and we can classify them, but we have no idea what they are made of or why they behave as they do. We are at the edge of a deep structure that we can sense but not yet see, and that is, in its way, a strange privilege. To be at the frontier of knowledge, not at the back of the classroom, learning what others have established, but at the edge of the unknown, where the questions are still open and the answers are genuinely uncertain. This is where science is most alive. It is also where it is most difficult and most frustrating, but it is unmistakably the most interesting place to be. The physicists and astronomers working on dark matter today are not just solving a puzzle. They are sitting with a mystery that has no solution in hand. They are learning to work in genuine uncertainty, not the provisional uncertainty of, we haven't checked the math yet, but the deep uncertainty of, we don't know what we're looking for. That requires a particular kind of intellectual courage. The courage to keep working when the answer isn't coming, to keep designing experiments that might come up empty, to keep revising theories in the face of discouraging data, to keep believing that the question has an answer, even when the answer refuses to appear. This is what science actually looks like most of the time. Not the triumphant moment of discovery, not the textbook synthesis of knowledge into a clean narrative, but the long, difficult, uncertain middle stretch. The years and decades of careful work, of instruments built and rebuilt, of hypotheses proposed and discarded, of brilliant people devoting their careers to questions that may not yield answers in their lifetimes. And it is important to understand this, not just as a description of how science works, but as an honest account of where we are. Dark matter is not an almost solved problem. It is a deeply open problem. The evidence is overwhelming. The answers are not in. We began with you standing under a night sky, with the ancient light landing on your eyes, with the 5% that you can see glittering against the dark. Let us end there too, but see it differently now. The darkness between the stars is not empty. It has never been empty. It is threaded with the gravitational tracework of something vast and invisible, a cosmic scaffolding that reaches from the Big Bang to the present moment, that shaped the first structures in the universe, that organized the matter that eventually became galaxies, stars, planets, and you. You are here because of dark matter. The specific chain of cause and effect that led to the existence of your planet, your star, your galaxy, begins in the gravitational dynamics of something we cannot see. The universe is not what it looks like. It never was. Or what we can see, the brilliant, luminous, optically beautiful fraction that has occupied our attention for all of recorded history, is the surface of a much deeper reality, a reality that does not care whether it is visible, that does not emit signals we can easily read, that exists in its own way, on its own terms, indifferent to the instruments we have built and the theories we have constructed to make sense of it. There is something humbling about that, and something clarifying. We often speak of knowing the universe, of understanding it, of science having essentially solved the structure of nature with only details remaining to fill in. Dark matter is the answer to that presumption. It says, you have solved the 5%. The rest is still waiting. But here is what I find most extraordinary about this situation. The fact that we know about the other 95, the fact that we can quantify it, map its effects, trace its history, simulate its behavior, the fact that we know it is there at all, is itself one of the greatest intellectual achievements in the history of our species. We have no eyes for dark matter. We have no sense organ, no evolved capability, no innate ability to perceive it. And yet here we are, aware of it, measuring it, debating its nature, building machines deep underground to listen for its touch, pointing satellites at the oldest light in the universe to read the imprints it left there, filling computers with simulations of its behavior across cosmic time, naming it, arguing about it, dreaming of the day when we finally identify what it is. The universe did not give us that. We reached for it. With mathematics and physics and engineering and patience and argument, and the accumulated effort of generations of curious people who could not stop asking what was out there. That is what we are. That is the kind of animal we are. Not the kind that accepts the limits of its senses as the limits of its world. The kind that keeps pushing, keeps questioning, keeps looking beyond what the eye can see toward the vast invisible structure of what is real. And so the story does not end here. It cannot. The question that Fritz Zwicky asked in 1933, that Vera Rubin clarified in the 1970s, that decades of experiments have refined and deepened without answering, that question is still open. What is the universe made of? We know the answer is stranger than we thought. Larger, darker, and more complex. We know that the reality we inhabit is mostly composed of things we do not understand. We know that the cosmos we can see is embedded in a cosmos we cannot, that the luminous web of galaxies floats inside a dark matter structure of far greater mass and extent, and that this structure floats, in turn, inside the expanding vacuum of dark energy, which is itself barely understood. We are not at the end of the story. We are in the middle of it, perhaps near the beginning, and somewhere, in a detector deep underground, in data from a telescope not yet built, in the mind of a physicist who has not yet had the idea, somewhere the answer is waiting. The universe has been holding it this whole time, patient as always, silent as always, vast beyond imagining, waiting for us to become clever enough, quiet enough, precise enough to hear what it has been saying all along. We are working on it. The darkness will not hold its secrets forever.